Hello, my name is James and this is my lab for circuits and capacitors. Alright, the introduction. So the description and purpose, the purpose of this lab was to better understand the properties of circuits and to use a multimeter to measure the current and potential differences of the circuits and predict its current and voltage within a circuit. The results were that the actual values of the current and voltage matches the ones predicted by the formulas, which being the node and the loop rules. And in an RC circuit, the magnitude of current is time dependent. Okay, so the fundamental principles that we used was the loop rule, which is the V loop is equal to all of the velocities combined. Node rule, which is I in is equals to I out. Ohm's law, which is change of V is equal to IR. Linearization, which we don't really have to use, but which is ln change of V over change of V initial equals negative time over RC. And resistance in series, which is R series, is equal to all of the resistances added. Alright, so the part one, measuring and predicting the current with the ammeter. So the system and surroundings were that the entire circuit and everything outside the circuit. And initially there was two batteries, both with 1.5 volts, plus a multimeter, which can be both ammeter and voltmeter, and with two resistors, which is 47 ohms and 100 ohms. And the expected versus actual current. So the expected was 0.0204, which was solved by this equation, which is the two ohms of the resistors added together, divided by 3, and while the actual was 0.02. Okay, so when the connection of the ammeter was reversed, the magnitude stayed the same, but it turned negative. And since only one wire is in each end of the nodes, the current through each resistor is the same. Okay, so this is the model that we use, and this is what we created in our lab. And you can see how we have the the two batteries here, the ammeter, and then the two resistors. All right. So measuring the voltage. So here's how we measured it from A through, I believe it's G, and you can see that from A to B we have 3 volts because it's 1.5 times 2 is 3, right? And then C to D, everything else doesn't matter, but most importantly, the resistors, first resistor, C to D, right here, we got 0.954. And the E to F, the second resistor, we got 2. So then after we do the equation of EMF minus R1 minus R2 equals 0, R1, R2 being CD, first resistor, and FG, so EF, second resistor, you get the result of 0.02A. Alright, so the graph of the voltage, if you grabbed it out, was in the beginning, we had 3 volts, and from A to B it rises up to 3, and then from C it just goes down because it's 47, and E because it's 100 is way more, so it goes down all the way, and it means 0.02. Okay, so the part 2 of the RC model is where we do the light bulb. See the ammeter and the light bulb here, and the model is the same thing but just with a light bulb added. And then what happened with the lights, the light dimmed after running, and after connecting the capacitors it turned on and they dimmed later. The current in the circuit started to slow down. When the battery disconnected, it began to slow and went opposite ways because of the capacitor, which inverted the electric flow. And lastly, the time to charge was for the 10 ohm bulb was about 3.3 seconds. The discharge was about 4.23, while for the 20 ohm it was around 6.21, and discharge was around 2.1 seconds. Okay, so the question, if you charge the capacitor with no resistor in a circuit, how quickly would our ideal model predict the capacitor to reach fully charged? So the ideal model would predict the capacitor to charge instantaneously because it's just ideal, but the wires inside the batteries and every other like different outside things would have resistance, so it would not charge instantly in the real world. Okay, thank you.